Today we are going over lesson 3.1, exponential functions and their graphs. Chapter 3 is all about exponential and logarithmic functions. So as you peek through your notes packet, you'll see that kind of early on we're getting into some graphs. What we do to run into some rules and properties of exponents, and then we kind of deal with the literally opposite of that, which is going to be properties of the logarithms. And then we'll get into some expanding and condensing properties, as well as how we can solve whether we need change of base or just to switch forms. Starting off, this is a basic look of a graph of an exponential function. Right? You'll notice clearly we've got an asymptote here, and that's usually if y is 0, or specifically k. When we get into our standard form of something like this, a times b to the x minus h plus k, right? That's a really fancy form. The most basic one we'll probably deal with kind of a times b to the x. But, right, if we think of something simple, like this one's probably 2 to the x, can we get this to equal 0, right? Well, if we do 2 to the negative 5, we get 1 over 2 to the 5, which is really small, but not 0. And we can keep getting smaller and smaller, but we won't ever reach 0. So that's why our asymptote horizontally is y equals k. Basically, in this first diagram, y is 0. Right? Natural exponential function. Reminder, we've got e is 2.7183. Right? I'll talk about where that comes from as we run into compound interest. So starting off, some basic questions, evaluate using a calculator, round to 3 decimal places. So these are things you should know how to do in your calculator, right? The power button looks like that. So the 4.2 for this one, and you would get 22.559. Next one, the cube root button, you can either find this one, which lets you say which root it is, or technically, you could also understand it a little bit that this is to the 1/3 root of 4, and you'll still get, when you multiply that by 315, 500.031. And lastly, e to the 5.2 is 181.272. All right, so again, popping up the calculator to show you where that button is. Again, e is e to the power is right here, second ln. There's also another E button over here from the division button. All right, so notice the button presses down here. Moving on, we've got what are the properties of exponents? So pulling them out, what does it mean? A to the n means we have a times itself n times. Right. A to the negative n is the same as 1 over a to the n. Next, if we're multiplying and we have the same base, we can add those exponents, right? X squared plus x to the 3rd. We just say how many x's do we have? 2 plus 3 equals 5, right? So if we can, if multiplying and we have the same base means we can add. Dividing means we can subtract. Moving on, what if we have a to the n to the nth power, right? So x squared to the 3rd power, meaning we have 3 groups of x squared. You could just multiply. 2 times 3 is 6. What if we have multiple things inside of the bracket? Both pieces get the exponent, whether it's a fraction or not. And lastly, anything to the 0 power is 1. Start off, we'll do some basic graphing. So reminder, 3 to the x. Right, in this situation, we're choosing the x, figuring out the y. So usually kind of do a 0, 1, 2, or negative 1, 0, 1. So 3 to the 0 is 1, 3 to the 1 is 3, 3 squared is 9, right? Giving this times by whatever our base is, right? Right, but again, we've got that horizontal asymptote at 0 because it's not plus a number at the end, right? So because there's no number there, that's why our horizontal asymptote is 0. And then a little note, how would that look different? Just a couple different options, right? So if we had 3 to the x minus 3, right, this would move us 3 to the right, because the question is how do you get back to 0? 3, so then that one would be right? Moving all these points 3 to the right. And you get the same kind of idea. Next up is negative 3 to the x plus 1. Now just a note, on the PEMDAS side of things, this is not negative 3 to the x, right? It's not in parentheses. So this is literally, what is 3 to the x? Then we're going to multiply by negative 1, and then we're going to shift it by the plus 1 outside. So again, transformation reminders. So this, if we took our same first key points from the beginning, right, negative 1 is on the outside, so it affects the y. So then our points would flip over this line, and we'd go negative 1, negative 3, negative 9. And then plus 1 is our k value and our asymptote. So we would be adding 1 to these y values to get negative 1 plus 1, 0. 1 added to negative 3 is minus 2, or 1 added to minus 9 is minus 8. So we'd end up with a graph that looks like 0, 0, 1, negative 2, and sorry, I goofed up my x out there, 2, negative 8. Right. And then the graph, because we had k is 1, there's our asymptote, and it'd be upside down. Now, most of the time, right after we get through this point, I just arrow down. But it doesn't hurt to know where the second number is going to be. Most of the time, if it's a base greater than 3, we'd already be off the graph, right? 4 squared 16, most of my graphs aren't greater than that value. Okay. Moving on, half to the x minus 1 minus 2. Instead of dealing with half, right, half is literally 2 to the negative 1. So we're going to treat this as 2 to the negative x minus 1 in the exponent minus 2. So again, what happens here with our key points? So again, this time it's 2. So looking at 2 to the x, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4. And now, what does that minus do first? We do the multiplying first. That one is next to the x and affects the x. So this is flipping us over this line right here, looking at our y-axis. So now we're going to be 0, negative 1, negative 2. And then our y values remain the same. And then this minus 2 at the end, right here, shifts us 2 down. So that's also our asymptote. Is y is minus 2 is our vertical asymptote. Okay? So subtracting 2 from these, we get negative 1, 0, 2. The x value stayed the same for that part. So 0, negative 1, negative 1, 0, negative 2, 2. Work a little off here. And we have a kind of a decay looking graph where we're going down something like that. Moving on, 2 to the negative x plus 1. Now, negative x plus 1 is not x minus h. So we're taking the negative out of both pieces. We get 2 to the negative x minus 1 minus 4, giving us kind of our hk values. And again, just like last time, 2 to the x, we're looking just at the parent function. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4. And just like last question, what does that negative 1 in front do? It's multiplying times the x values. And then, after we do that, y values stay the same. And then we deal with opposite, which would be plus 1 to the right, minus 4 down, right? Opposite of what's next to x, take what's outside. So then, once we have these points, again, technically, just real basic marking here, those points shifted this way, again, flipping over that y-axis, and then we're going 1 right and 4 down. So our asymptotes went 4 down as well. And 1 right, 4 down, 1 right, 4 down, 1 right, 4 down. Those are my points. Which again, if I did that, we have 1, 0, negative 1, negative 3, negative 2, 0. It looks pretty accurate. I have negative 1, 3 graph, 0, negative 2, negative 1, 0 are my key points. So you do need to know your transmutation rules from 1, 4. We use those a lot in that one. Next, formulas for compound interest, right? A equals P times 1 plus R to the over N to the NT. Now, as 1 plus 1 over N to the N gets really large, say N goes to 1,000, we get E. So that's where the compound, continuously compounding one, becomes PE to the RT, which stands for the number about 2.71, keeps going. Kind of like pi, but it's on your calculator. This Euler's number, because he's the one that came up with it. But looking here, right, reminder, P is our amount of money, or our starting amount. R is rate, written as a decimal. So they might tell you like 3%. Well, then we would write that as 0.03. N is the number of compounds per year, as it's written right here. So if they said annually, that's once a year, monthly, 12 times a year, right, so on. And then T is number of years. Right? So you'll notice we have rate, T, and P, and both of them. On the left, when they have options for how many compounds per year, they'll have to give you information for that, right, to give you the N. So starting off, you invested $20,000 at a rate of 7% for 12 years, compounded N times, where they give you a chart for what N is. What is the balance after 12 years? So again, we've got this one, because they didn't say continuously compounded. So here's what we have, fill it in. Rate of 7%, we're going to write that as 0.07. For 12 years, T is 12. $20,000 is P, our principal. Right, principal, right, money's our pal, some people have said. And then filling it in. This is kind of what I have. So there's a couple ways to do this. You can grind this out on your calculator. Plug in N equals 1, that's fine. So I'll show you that for a couple problems, a couple pieces. So again, just trying to show you shortened ways to do this. But when we plug it in, we've got 20,000. Oops, I got my E in there, sorry, 20,000 times 1 plus 0.07. And the first one was 1. Now clearly, if you're doing the math in your head, you're probably like, we just leave it as 0.07. However, for extra button presses for the next time, I'm typing it in and we get $45,043.83. Now to make the second one quicker, because the next one is 2, I hit second enter on my calculator. That repeats what I just wrote in there, and I just need to go back and change my 1s to 2s. This is one way to do this in a slightly quicker way. I get $45,666.57 for that. Right? And then one more time showing you second enter, changing those 2s to 4s. Now it gets a little more complicated when you get to, the next one would be 12. Oops, I had 4 twice here, so I'm going to close that parentheses. All right, so just a quick example, we'll hit enter, talk about how you'd have to do it with 12. So we got 45,991.97. So with 12, right, I'm going to go to the left here first. Or if I do 12, it just overwrites, and I pretty much need another parentheses. Now, fortunately, I can just write over it, and then it'll be like, hey, we need a parentheses, which is kind of what it was doing there, and that just worked fine. Sometimes you'll have to do the insert button, which is right above delete, so you hit second delete, and it will let you add spaces, right? So then it'll write without overwriting, right? It won't delete the 4 that we have in front of it. So this one, 46,214. One more time for 320. I'm going to show you one more way to do this. Technically, it doesn't matter which 12 we overwrite, but we'll move it on the outside here. And there's definitely a mistake in there. Oh, I did 3220. Okay. We gotta fix it. Right. So notice, I was not expecting my answer to be like also 9 million billion or whatever it is. That large of a number. Right. There we go. Now it looks similar to what we had. Because again, it's not really increasing. Right. If you think about what's happening on with the math, they take the percentage and chop it by the same amount of compounds we're going to do. So it's like, oh, 3.5% 2 times a year is more than 7% 1 time a year. Because eventually, the more compounds you do, generally the more money you'll get. However, it's not going to go to infinity, as you'll see. So then the last one was continuous. So now you have to actually type this one in, 20,000, and then second log button, sorry, not log, second ln button. Give this e to the, and now you're putting 0.07 times 12 years. And this is calculating as if we've done it multiple times. I'm not sure why it's double typing for me here. Let's happen a couple times. There we go, 46,327. Now you'll notice there wasn't a giant leap from 320 to continuous. Because again, at some point those gains taper off, right? Early on it's a big jump, but whatever. We start at $45,000 and we're almost 1,300 past that, not quite. So, just kind of being aware of that. Secondly, how can you do this? Graphing, right? 20,000, parentheses 1 plus 0.07 divided by x, because that's what's changing to the 12x, right? And then you would need to make your window large, like we went 0 to 320. So my x math might be like 365. Most of the rest of these don't matter as much. Again, 0 to, in the end, we already knew our numbers were around 50,000. 500,000, double typing, whatever. But as you see, that's exponential, but it doesn't look very exponential because it kind of stays put when you put 500,000 in instead of 50,000. Right, there's a slight increase and then it tapers off. Mine keeps double tapping here, so. There we go. So as you can see, there's a tiny bit of an increase at the beginning there, and then it tapers off. So how can you use this? Second trace for plugging in value. Sorry, I wrote 0. Second trace, plugging in that value, and then I can plug in x is 1 equals 45,043.83 cents. X is 2. As soon as I write that down, 45,666. Right. So this way is a little quicker than the last one, because I didn't need to keep hitting it. It knows like, hey, we're still in plug in the x value mode. And there we go. We got all our answers there. So I'm just going to put mine rounded to the nearest dollar. But normally we would go to the nearest cent, because that's how our cash works here in the U.S. And there's that. So if you have any questions, let me know. Moving on, we've got a population problem. Population of a town increases according to the model 2500e to the 0.0293 t, where t is the time in years, and 0 represents the year 1990. Find the population of 92, 95, 98. So using 1990 as 0, right, technically you're doing this quick math in your head, like what real values am I plugging in, and you get t equals 2, and then you'll figure out what is it on my graph, right, or plugging it in. T equals 5, what is my value, and t equals 8, what is my value. With only 3 of them, we could type it in the calculator, or you could graph it. Either way works. Just to show how the graphing works one more time. So we have 2,500, second ln for the e to the, I think get my second, oh, I hit it twice again, 0.0293, aerial button, which is x, and then again my window is going to need to be adjusted a little bit. We're only doing, if you read further on, up to probably year 25 at the most. And since we're at 2,500, we're not going to exactly shoot through the roof. So we'll go to 5,000 about. Okay, so graphing it, we can kind of see a little bit there. And so then we're doing second calc for trace value at year 2. We have 2650.8. Well, it doesn't make sense to have 0.87 of a person. So again, we're just going to round that up, so 2651. And again, having calculated this out ahead of time, same thing with the other 2 numbers, 2894 and 3160. Make sure you know how to do this in your calculator. We're not going to answer calculator questions on the test. You got to know how to use it. Use the graphing utility. Yep, we did that. Now this is why we needed to go to 25, right? It's minus 1990 here. We get 25. So that's why I went to 25 years, because it wants us to approximate 15 and 20, right? What about t is 15, t is 20? Not really approximate. It's actually calculate in our calculator. And when you plug that in, we get 3880 and 4492. Same method we did for plugging into 5 and 8. Okay, moving on to the last set of slides. Half-life. You will need to know this formula when it comes back later in the year. So half-life is, we've got, let Q in grams represent the quantity of radium, which has a half-life of 1620 years. The amount of radium in 226 was 25 grams. Write an equation to represent the amount after T years. So we've got quantity left over equals, usually they use I for like initial amount. That could also be principal, but it's not money this time. And half-life is how long it takes for it to literally like disintegrate or kind of decay by half. To the T over half-life is our formula. Right? So how many years divided by the half-life? So plugging in our information, 25 grams is our I, and our half-life number is 1620 there, so Q equals 25, parentheses, half to the T over 1620. Determine the quantity present after 1,000 years and 2,000. So T is 1,000, T is 2,000, and it's asking us, again, if we read ahead, to graph till 5,000, and then will it ever get to 0, right? So, things to be thinking about, we're typing it in, and 25 times, you can do 1 over 2, or I like to do 0.5 to the x divided by 1620. I need to change my window because we're dealing with a lot of years, right? Up to 2,000 years, or actually 5,000. And our maximum value is going to be less than 30. So plugging it in, and that's a decaying type function. So second trace value, what's it going to be at 1,000? 16.297 grams. What about after 2,000? $10.624 grams. We already graphed it. When is it going to reach 0? If you're dividing something by half, even if it's as small as like $1, you're technically going to keep getting fractions of a penny before you're going to get to 0, right? You're never going to get 0. So never, this is technically our horizontal asymptote. So that's why we won't get 0. Last graphing thing, using your graphing utility, find the intersection of 20e to the 0.05x and 1500. So this time we're going to need doing this. Let's see. We'll guess it's within the first 200 that we're going to go from 0 to our y value is 1500 on the other one. So I just need a little bit above that. We'll call that 1600. I generally don't fill in a lot of these other values because just little tick marks on the graph. Not a huge deal to me because we're not doing this out, but we've got 20 e to the 0.05x, and then we've got 1500. Graph them. How do I find the intersection? It's always been the calc button. Second calc, intersect is number 5. Okay, so again, double typing for me, sorry. Not sure what's going on with the smartboard. Oh, we have x at 100, we're above the spot. We need, oh, there we are. And so you're estimating where that intersection is. You got to hit it 3 times, so I'm going to go on one line, on the other line, and now it's telling us our intersection is 86.3497, which rounds up 1500. So that's a temporary way to find our answer. There's our intersection. Again, that was second. The trace button, which is calc. Intersection, or intersect with it. abbreviated on mine. That wraps up today's lesson. As always, let me know if you have any questions.